So here we discussed about the induction and energy transfer. Energy transfer. So here we have a rectangular loop of wire of width L. So this is the width. This is the width. Has one end in a uniform external magnetic field that is directly perpendicular into the plane of the loop, into the page. So this field may be produced by a large electromagnet. So the dash line, is the assumed limit of the boundary of the magnetic field. The fringe of the field at this edge is neglected. So you are to pull this loop to the right at a constant. So we try to pull it to the right side, So and you can consider the magnetic flux. The magnetic flux is to this loop is decreasing because you are moving this loop out of this magnetic field, uniform magnetic field. So the magnetic flux is decreasing. So it will generate a electromotive force which is decreasing, which means you need to it will generate a electromotive force pointing into the page. Yeah. So EMF should be clockwise. Because originally it is into the page and then you decrease it. So this one need to counteract this decrease of the magnetic flux. So it should be clockwise. The current should be in this direction. And actually, you can see that as long as the current is in this direction, and in this direction. So there will be Lorentz Force. You still remember the Lorentz Force? So it should be somehow like I dl cross B. IDL cross B. So for the left hand side run, so DL point to the upper side, and then the B field point into the page. So it's somehow the F1 should point to the left side, and for the lower wire, BL point to the right side, and then B into the page. So F3 point to this side. So for the upper one I point to the right side, and then R cross B, F2 point to this side. So actually F2 and F3 will cancel each other, and F1 point to the left side, and then you try to pull it out, but it try to pull back, which means that you need to have some work done to really pull this loop out. So their flux change. So therefore, the magnetic field and a conducting loop are in relative motion at speed v, and the flux of the field through the loop is changing with time. So to pull the loop at a constant velocity, you must apply a constant force F to the loop because a magnetic force of the equal magnitude but opposite direction act on the loop to oppose you. The rate at which you do work, that is the power, is then this one. So which is actually the F times V. Yeah, because you should have learned that uh, oh, actually you should have learned that W should be Fs. W should be Fs. So, and more generally, you can write it as W equals F dot ds for a contour. And actually, P should be dw ds. dw ds. So you can consider. This is nothing but if f is constant, so it will be somehow like not ds, dt, should be dt. So ds dt. So you just substitute w equals fs here, and f is assumed to be a constant, and then it is factor out. So it is ds dt, and this one should be fv. Okay, so now we consider how to quantify all this stuff. So we know that phi b is BA. Well, at any moment we assume that yeah, actually the B is uniform. The B is uniform. So BA is BLX. L is the width, and X is this one, Actually, this part inside the magnetic field. Actually, you are pulling out, so X is decreasing. So as X decreases, the flux decreases. Faraday's law tells us that this flux decrease and EMF induced in the loop. We can write the magnitude of the EMF as this one. So this is the Faraday's law. And then we substitute this one here, and B and L are constant. So we can factor B and L out, and then dx dt is nothing but the V. So we have the electromotive force to be BLV. So next one, we consider the equivalent resistance of the loop is R. So yeah, so we have BLV to be the electromotive force, and then we divide it by R. So this is the current. This is the current. And I just mentioned that we have F1, F2, and F3, and F2 and F3 are equal and opposite, and in opposite direction, so that they are cancelled. So this leaves only force F1, which is directly opposite to your force on the loop, and thus is the force opposing you. So I just mentioned it. You try to pull it out from the magnetic field, and then this force will try to pull it back. So actually, you have done some work, and they will generate some electromotive force inside. And actually, this electromotive force, there will be a current, and then go through the resistance. Then there will be some power. I square R. So as long as we know that F1 should be ILB sine 90 degree, they are perpendicular to each other. So which is nothing but ILB, and this is I, what we have derived in the previous page, and then we substitute here. So we have B squared L squared times V over R. So this is the force. Yeah. So and finally, P equals FV. So this is pretty nice. So B squared L squared V squared over R to be the power. So we'll find that the rate at which you work on the loop as you pull it from the magnetic field is like this, and the work that you do in pulling the loop through the magnetic field appear as thermal energy in the loop, because it's all consumed by this resistor. So IR squared will turn into heat. So any question up till now? So next we talk about the eddy currents. Wo. In Chinese it's called wo. So as you pull a solid conducting plate out of a magnetic field, eddy current are induced in the plate. A typical loop of eddy current is shown. Typical loop. So just now we have a concrete loop. So you can consider there will be some current going through a specific loop. Here, it is a plate, a conducting plate. But actually, even if you just pull out a conducting plate out of the magnetic field, which is perpendicular to you, then there will be some eddy current inside this current loop. So as you pull a solid conducting plate out of the magnetic field, eddy current are induced in the plate. A typical loop of eddy current is shown. Yeah, so using the induced electric field, we can write Faraday's law in its most general form. So actually, this is the more general form of the Faraday's law. Just like for the Gauss law, you can actually write it as phi E equals epsilon naught equals Q enclosed. But actually you can write this one into a surface integration. And similar for this case, the electromotive force can be written as a line integral. So actually, the concept of the electric potential should be used very carefully here, because you can imagine here we have electromotive force, which means that we don't necessarily go for a loop and then it turns out to be a zero. It's something like that. So we need to really consider this loop is not zero anymore. For electrostatics, this line integral should be zero. This line integral should be zero. Because at that time we defined V to be E. Do you still remember this one? So this is the electric potential difference between A and B. So at that time, as long as there are no varying B field, then we can have the voltage potential like this. As long as A and B are the same point, then this one should be zero. But here is not the same case. Here is not the same case. As long as varying B field, and then we integrate E dot ds for the closed loop, ambient loop, or what closed loop, then this integration is not zero anymore. So a changing magnetic field produces an electric field. So you can imagine here, copper ring. So it is electric field line. So you can imagine there is a magnetic field pointing into the page, and suppose this B field is varying, it will generate a electromotive force or eddy current inside this copper ring. So you can imagine this one is counterclockwise, which means pointing out of the page. So you can imagine this magnetic field is increasing. As long as the magnetic field is increasing, the net change is into the page. So the induced EMF should generate an induced B field pointing out of the page. And using the right-hand rule, you know that as long as it is counterclockwise, it is out of the page. So this is actually the E field. The E field. For this point, the E field point to this side. For this point, the E field point to this side. The E field point to this side. At this point, the E field point to this side. So as long as you integrate the E field along this loop, it is not zero anymore. So induced E field are produced not by static charge, but by a changing magnetic flux. Therefore, electric potential has meaning only for electric potential has meaning only for electric fields that are produced by static charges in electrostatics, just for what I mentioned. It has no meaning for electric fields that are produced by induction. By induction. Actually, as long as you learn in electromagnetics, you should have known this one. E equals V like that. And I'm not really sure whether it's like this. Well, there should be another term called A to be the potential for the magnetic field. For the magnetic field, I'm not. And then as long as you take the curl of this magnetic potential, then it will turn to the E field somehow like that. I don't really remember. But actually, you can consider the electric potential somehow like that. But you need to use it very carefully. So here, if the magnetic field increase at the static rate, a constant induced current appear in the copper ring of radius r. So I just mentioned if this one increase. Okay, so for B, an induced electric field exists even if the ring is removed. If the ring is removed. So it just go for a circular path. So the complete picture of the induced electric field display as field line. So there will be many electric field lines. So four similar closed paths that enclose the identical area equal EMF are induced around path 1 and path 2. Because it enclose the same area, and actually the magnetic field is uniform over this area. So the rate of change in this area is the same for path 1 and path 2. So which means that the EMF for this path, for path A and path 2 are actually the same. But for path 3, half of the loop are outside, and roughly half part of the loop are outside. So the EMF for path 3 is smaller than path 1 and path 2. Only partially lies in the region. So for path 4, this loop is totally out of the region, which means that so for the right hand side of the Faraday's law, it should be 0. So that this integration should be 0. The E field doesn't necessary to be 0 for the whole path, but the integration for this loop should be 0. So no net EMF is induced around path 4, which lies entirely outside the magnetic field. Therefore, an EMF is induced by a changing magnetic flux even if the loop through the through which the flux is changing is not physical conductor, but an imaginary line. The changing magnetic field induced an E field at every point of such a loop. The induced EMF is related to this one. So this is the induced EMF. So in the physics textbook, is this one line to use the E to stand for the EMF, and sometimes this is equal to minus V in circuit sense. Okay, let's consider a sample problem. So in the figure, take R to be 8.5 centimeter dB dt. Like this one, find an expression for the magnitude E of the induced E field at point within the magnetic field at radius out from the center of the magnetic field. Evaluate the expression for R. Well, take R to be the large one. So here we consider E dot ds and take the integration. So we always assume, so as it is a circle, and it is symmetrical. It's symmetrical. So because this circle and the whole circle should have a same center, so we'll assume E should always have the same direction as ds, which means that it should be nothing but E ds. And E should be a constant, so it is nothing but this one. And then this is the length of a circle, so it is nothing but 2 pi r. And for phi b, which is BA, as yeah, and we want to consider d phi b dt. D phi b dt is nothing but d BA dt. Actually, A should be a constant, and then we can just factor it out. So it is A times dB dt. So A is nothing but pi r square, and then dB dt is 0.13. So now we can have the Faraday's law like this, equals negative dB dt d phi b dt. Phi b dt. So we will have on the left side E 2 pi r equals 0.13 pi r squared. So pi and pi can be cancelled. R can be cancelled, one of them. then we forgot the minus sign. So finally, we have E equals minus 0.13 over 2 R. Well, actually, you can write it as 0.065 R. Okay, so actually, when we consider the magnitude, E should be 0.065 R voltage per meter. A volt per meter. And then if we substitute R equals to actually if we substitute E for R equals to 5.2 centimeter, then this one should be you multiply R by 0.052. So this one should be 3.4 millivolt per meter. So this M is milli, this M is meter, so they cannot be cancelled. So, so this is E. Okay, so next, we consider. So next we consider find the expression induced V upon P. So we find the E field out of this one. Out of this one. Because R is only 8.5 centimeter. But we find the E field out of this out of the B field. So for this case, R should be larger than capital R. So now we have a d phi b dt to be 0.13 pi r squared rather than small r. For the previous case, we have phi b to be this one, 0.13 pi small r squared. But here, this is not small r squared anymore because out of this region there are no magnetic field. So the only magnetic field is inside the yellow area, which is 0.13 pi r squared. And actually, using the Faraday's law again, minus 5 d phi b dt. So for the left-hand side, it is still the same 2 pi small r, because we need to consider the closed loop like that. This is the loop. So we need to consider small r here. But for the right side, it should be 0.13 pi capital R squared with a negative sign. So E should be minus 0.13 over 2. Here we have small r and then r squared. And as long as we take the absolute value and then substitute all the numbers. 0.132, R is 12.5, which is 0.125 meter. And then R is 0.085 square. So actually E is, we do not substitute the R, small r yet. We just keep the R here. Just keep the we keep the R here. We keep the R here. So that E would look like 4.7 times 10 to minus 4 over small r. V per m. V per m. And then finally, because it asks for the expression for the at radius r, so we need this one first, and then we substitute E for r equals to 12.5 centimeter. And as long as you substitute R equals to 0.125, so the answer will be 3.8 millivolt per meter. Slightly smaller than, slightly larger than the previous one. But actually the E will decrease as R increase, but only proportional to the inverse of R. Proportional to the inverse of R. Here, for the inside part, it is proportional to the R. Proportional to the R. But for the outside part, it is inverse proportional to R. Okay, an inductor is a device that can be used to produce a known magnetic field in a specific region if a current I is established through each of the n windings. So of an inductor, a magnetic flux phi b should be like this. So this is a definition of an inductor, or of an inductor, of the inductance. So it counts about the magnetic flux to the coil and normalize it by the current, and it should be a constant. It should be a constant. And actually, the SI unit for the inductor should be Henry. Should be Henry. Should be Henry. So actually, N phi B is the flux, is the magnetic flux, and phi B would be BA if you assume the phi B. This is phi B. If you assume the magnetic field is uniform, and N is the total number of coil, and so this small n is the number of coil per unit length, and L is the length of the coil. And as we learned in the previous chapter, B is mu0 IN for a solenoid, and we substitute this one into here, so we have the determinator like this, and as long as we divide L on both, small l on both sides, So this is the inductance per unit length, and I can be cancelled. So it is can be simplified like this. We have n here, we have n here. So we have totally n squared. So the inductance per unit length is, this one is a constant, mu0 is a constant. So it is proportional to the cross-section area, and proportional to the square of the number of coil. So as long as you have more coil, then the inductance can be much larger, rather than increasing the cross-section area.